the mic on? Can you hear me? All right, so shall we get started? How was the exam? You hate me yet? Was it long or short? Was it too long? I don't know. I haven't talked to the TA, so it was okay? Did you feel like you could get through it in about 50 minutes? Were there any surprises? No? Some? Surprises are good. So let me remind you where we are and what I plan to have done by the time you get back. So homework 1 is due by midnight tonight. You all know that. I think the TAs have been keeping up. I was away. I left Tuesday morning at 6, and I got back last night about midnight. So I haven't really been keeping up with Piazza, but I think the TAs have. So I'll go in and read them this afternoon and make sure there's nothing that doesn't need my immediate attention and let the TAs finish with the Piazza requests. There's a 24-hour grace period, so you can turn in your homework up to 24 hours late. There's a 25% penalty, meaning that you can't do better than 75%, not meaning that your score is reduced by 25%, meaning that, nobody's going to get, you may not get 100% anyway, right? So if you think you can get closer to 75% by waiting 24 hours, it's well worth your time. So it's a cap, not a scale. We'll start question of the days again after the break. I wouldn't give you one to do over the break. You guys need a break. I need a break from grading. We'll grade over the break with the midterm. They're on my desk, so I'll scan them in today and we'll start grading them. Those should be done over the break. I'm not going to go over answers today because I feel better to go over it after you've seen what you've gotten done, right or wrong, on your exam. So you'll be able to access those through through the ICON website when we're done. And then after midterm 2, a week from Monday, when I see you again, we'll do the answers to midterm 2, and I'll release a scale of your grades so far. So both midterms, all the questions of the day, the labs, and so on, it'll approximate your final grade where your standing is now. Unfortunately, we probably will not have homework 1 completed by that Monday. If we do, that'll be included, but if we don't, that'll come later. Questions? Okay. All right, so where were we? We're going to push forward with our word ladder problem. Let's review what we were talking about before the exam. Before the exam, I gave you 3 different mechanisms to read data from a file. In this case, strings or text from a file. Remember, we have this list of 5,757 words that we want to read in and use as the sort of underlying structure for our word ladder game. And I showed you that the 3 ways pretty much reduce to using a read statement, the read method for the object of type file handle. So we use open to open this file for reading. That returns an object which is a file handle, thing you can manipulate. And that object has a bunch of methods, including the read method, which reads in the whole file into memory and returns it as a string. So we can look at the string S and 34,000 some odd characters. I can look at the first 20 characters and I see they are new line separated 5-letter words. Kind of what I expected. I can use the split method of string to turn it into a list of words, and there's my 57 words. And the first 4 words are these. And then I clean up after myself by closing the file. So solution 1 involves opening the file and reading it all in one fell swoop, which is great if the file does not overwhelm your system, right? If the file is the text of the Encyclopedia Britannica, even that's not that big anymore, but imagine that's what it is, or the collected works of Shakespeare, you might not want to read the whole thing at once if you're just looking to see, did he use the word Cleopatra, for example. So option 2, oh, for heaven's sakes. So option 2 is to read in each line in the file one at a time. So the same thing happens. We open the file for reading access. That returns the file handle. but instead of the read method, I'm going to use the readLine method, which it reads in one line. And by iteratively calling readLine, I'll read in one line at a time. Sorry, my lips aren't working. I probably slept 5 hours yesterday, so I'm a little bit behind here. So readLine just returns the first line, which is separated by the new line and includes the new line character. And if I want to get rid of that new line character, the easiest way to do that is to use the strip method on the string that's returned by readLine to get just the word. And notice each time I call this, I'll get the next word in the file. Beware of one thing though. This is a very handy method of concatenating method invocations. So this is a file handle. Its method is a readLine method. The readLine method returns a string, so this method must be a method for the string object, not for the file handle object. So this concatenation of methods, remember each method returns something, and the next method invocation must be valid for that type of thing that was returned by the prior method invocation. So just because the first thing is a file handle doesn't mean that the chain of methods is all for file handles. The first one's for a file handle, but since that returns a string, the next method is a string method. Does that make sense to everybody? These chains of, these kinds of chains of method invocations, they're kind of common and more common in some languages. If you've written JavaScript, you recognize this. It will seem very natural to you. For some people, these are not natural at all. So I don't mind chains of method invocations. I actually think it's an elegant way to express a single thought. I look at this and I see, oh, I got a file handle. I'm going to read a line and strip off the end character. Looks perfectly natural. But as these strings of methods get longer and longer, they get more and more obtuse. So it's a balance, right? Don't make it, it's not a game to see how many you can string together, right? 27 method invocations strung together is not particularly useful or readable. Yeah, Trevor.
What happens if you don't close the file?
That's a good question. So the question is, what happens if I don't do the file close? And there's a couple of answers. First of all, when I start Python, I have a running process, and I open a file, that file handle is associated with my running process. So when the Python session ends, that file handle will be closed. So you don't have to worry about it staying on in perpetuity. It ends when Python ends. However, there is an intrinsic limit in the operating system for how many file handles you can have open. And in the very unlikely event you exhaust that limit, you're going to have a problem. This is sort of the second part of this. And the final part of this is I'm opening this file for reading. The other ways of opening a file might be to write to a file or append to a file. And if I don't close the file, the way you write to a file is it often goes to a memory buffer, and then it gets written out as convenient to make the operating system more efficient. If you close a file that you're writing to, if you close it abruptly by letting the process end, the operating system may not have flushed the last characters. So there's a safety aspect when you're writing to make sure you close the file. It is very good practice to remember to clean up after yourselves. These are things that are, these kinds of assumptions, leaving file handles open and not worrying about it, that's the way bugs that can cause security issues happen in the first place. Right? So clean up after yourselves. Leave your room neat like your mom and dad used to ask you to do. Okay, so this is method 2, reading in one line at a time. And then here's method 3, which is an extension of method 2 that instead of explicitly invoking the readLine method, it uses the infile object. This is the file handle object. It uses it as an iterator. It treats it like it's a sequence of read lines. And the read line is implicit in here. I write the for loop that says for line in infile. Each time through the loop, line will be a successive value returned by read line. All right? I could do this for character in that thing if so the thing that's returned here, it depends on the object, how it reacts to being treated as an iterator. Here it's treating it as a line, not just because I write line, that's what the object does. And so when I invoke repeatedly line in infile, it will return a line each time. This is really no different than the second method, except it's much more elegant to read it this way. And I'll show you another way to make your reads and writes a little bit more elegant as well that gets rid of the problem of remembering to close the file. I'll show you that shortly. Otherwise, this works as expected. For every line, I'm going to append the result of stripping that line, and I start with an open, just an empty list, and I append each word successively to that list. At the end of the day, I have my list of words. All right, so here's the result of my coding. My read word files takes an optional file name argument. It opens a file name for read. I'm going to use the read the whole file. So this is a method of type file handle. And then this thing returns a string, which I will split, and this whole thing returns a list of words. It's not very long, so I'm just going to do it in one step. I'm going to close the file, and then I'm going to print some helpful output for the user, and I'm going to return the list. Now, this is a function you don't really want to invoke at the REPL. Because if you just type this function invocation at the REPL, you're going to have to wait while the read-eval print loop prints out 5,757 words, because that's the value that's returned. So typically, when I invoke this, what I'm going to do is I'm going to take read words and let it default to file name. And instead of letting it print out its 5757 words, I'm going to assign the result of read words to a variable w. And if you remember, this returns the list that I created here. So by doing this, I conveniently capture the list of words I've read in from the file, but that leaves, because this assignment here returns what? What does assignment return? Anybody remember? Returns none. It always returns nothing. Because it assigns to W, but the value of that assignment itself is none. It's nice to have a printed statement here that gives the user an idea that it actually did some work. Otherwise, you type W equals read words, and all you get is the new prompt. It's kind of nice to have some visceral feedback. And that comes from a print statement, right? So this line here is the output of the print statement that's embedded in the function call. It is not the result of the assignment. The assignment returns none. So some of you are still struggling a bit with the difference between print and return. Just because you print something doesn't mean you can capture it. When you return a value, you can assign the output of that function, the returned value of that function, like we do here, to a variable and capture what the function returns. Print is not capturable. It just goes to the screen and you see it. So I use print to give feedback, but I capture the return value with assignment. Sorry, where are we here? Okay, so the construction of the print string in my function looked like this. And this is kind of ugly, right? Because I have to take the length of W and convert it to a string and then concatenate it to a string with a space, explicit space here to make it all look right, just to print this statement. And there should be a better way of doing that, and there is. There's actually multiple better ways. I'm going to show you one of them. Some of you may have discovered other ways you'd prefer. But this is the one I've grown up using, and I think it's probably the most reasonable one to learn. You can read about it. I'll tell you, the chapters are here. I think it's 13. You should probably read that chapter. I'll put it on your assigned reading list. So we're going to use a method for strings called format. And this method basically takes a string that has some markup in it. So markup are symbols that you don't really want printed as part of the string. But there are things that tell the string what to do. So we've seen some markup already. \n is an example of markup in that string. It forces a new line. Here we're going to use a different set of markup. Yes?
That's chapter 13. Is that in Python?
Yeah, I think it says on the next slide. I'm doing the chapter number by memory, but just hang on just a second, I'll show you. So what's nice about this format method is it lets me specify exactly how some things should appear. So for example, new line always appears as a new line. There's not many ways you can create a new line. But if I want to print out a floating point number in my string, do I want all the digits of precision, or do I want just 1 or 2 digits of precision? How do I want it to look? And format allows me to control that. Chapter 16, there you go. Okay? 16 of Python for Everyone, or 14 of Think Python. And this format operator has a little language embedded in it. It's like a separate programming language. Those of you who've written C before will recognize some aspects of this. Not a lot. A lot of different languages have similar formatting languages. Now, I will caution you that Think Python and Python for Everyone describe an older version of the format method that's introduced with a % sign. We're going to use the explicit modern 3.9 version that uses an explicit call to format. So if you really want the skinny, go to this website. This website, by the way, should be bookmarked by all of you. This is the Python documentation website. It's the latest word, and in a sense, it's the one true source for how Python works. All right, so here's the basics. You recall what I had in that statement is I had the length of W turned into a string added to this text. Here I'm going to have instead a string, this is just a string, with 2 special characters, the curly brackets. And these curly brackets indicate that that's like a fill in the blank. It's like Mad Libs for strings. You're going to fill in that blank. This defines a blank with something. So there's my string. There's the format method invocation, .format. And then the arguments to format get mapped to each of the Mad Libs blanks. So you see here my length of W, this thing right here, gets evaluated as an argument to the format method. This will return 5757, and that integer will be automatically converted to a string and inserted in the slot. Now this doesn't look like much of an improvement for our simple print statement, but when you're doing something like laying out tables, if you want to lay out tables of values with columns, this is incredibly useful. And you could just put it in a loop and it'll print out your table and everything will align. And all the formats will be the same, and every floating point number will be 2 digits of precision. And every string will be padded on the left by blanks so they fit nicely in tabular. There's all sorts of commands you can use to really, really control your output. So here's my final version of the read words function. It's all the same. Let's review. There's a header that gives me the description of my function, the specification. I'm using a default value for a file name argument so that it looks for this file if I don't specify a file name. I open the file for read. I've got some nice inline comments that tell me what each step is doing. I have a document string here, which is a 3-quoted string that is what Python will look for in response to the help function applied to read words. It will print out this. And then I have a format which gives out some sort of nice user-oriented output and returns the list W, which I can capture as the value of read words. Okay? Yes?
Are you okay if we use F-style format?
Yeah, I'm okay with essentially the same thing, right? These are all facets of the same underlying system. There's this thing called F-strings and F-style formatting that are really just shorthand for the syntactic sugar for format. So if that's what you prefer, I don't have a problem with it. I actually like this method better personally for me because it's like, you know, I say, okay, I can see the physical mapping, the way it's done, but I don't really care. I do prefer you use format rather than trying to construct each string from scratch using concatenation. This, I think, is a superior method, and F-strings are as well. All right, so we're done reading in our words. What's the next step? Let's review. The whole point of the game was to build this network so that I could solve the laddering problem to go from a source word to a destination word via a series of single letter exchanges. Remember that game we were going to play? So the next step is to build the word network that is going to be the data that supports my solution mechanism. So what does that network look like? Well, I'm going to do this twice. The first time, I'm going to represent the network as a list of words, a list of lists of words, to be more precise. So I have a list of the words, all 57 words in my dictionary. And what I want to do is, so I have that list, and they're in alphabetical order. Remember, they're all alphabetized. And what I want to do is I want to create a second list where each element of that second list is a list of words that differ by one character from the corresponding word in the first list. Right? So I have a list of words, and I have another list of lists of words where each word in this list, the word in the ith position in the first list, has in the ith position in the second list a list of all the words in the dictionary that differ by this word by one character alone. Sorry. So I was at, I don't know if I told you where I was going. I went to see my mother. My mother's 94 and she lives alone. So I went down to see my mother because she needed some things in the house. At some point, she's nuts enough to go up on the ladder and change a light bulb, which is just crazy because she's 4'10". So the ladder has to be a tall ladder to reach the ceiling, and she's 94, and she's also kind of blind and mostly deaf, but and extremely stubborn. So I went to see my mom, and then I went to give a talk in Bloomington. So anybody been to Bloomington, Indiana? So this is it's a stunning campus if you go. It's quite beautiful. And I went to give a talk there, but then I had to drive back yesterday. That's a long drive, and it was crappy weather, so I got delayed on the way back. It was kind of a pain in the neck. That's why I'm not particularly pulled together today, and I apologize. Okay, so each element of the second list is the list of neighbors of the words in the first list. I'm going to just use a comprehension. My second, the comprehension that gives me the internal elements of the second list, basically says for every neighbor, collect every neighbor in the original word list if my current word, the corresponding word in the first list, is a neighbor to this word. So let's take a look at what this looks like. I have the make network function. I have the header that tells you what I'm doing. I pass to it a word list, which is my list of 57 words in alphabetical order. And then for every word in that word list, I'm going to collect the list of words that are neighbors to that original word. So it's a nested comprehension. In one step, it gives me this list that in corresponding locations is the list of neighbors for each word in the original list. It's really pretty slick, right? And then I'm going to print out some stuff just to make people feel like it's done something. I will return my network, which is the second word list, the nested list. But I'm going to print out blank words and blank edges in the networks, where the length of the word list tells me how many words are in the network, and the sum of the length of each network divided by 2 gives me the number of edges in the network. So can somebody explain this to me? Let's see what it does. For every element node in the network, for every node in the network, for every word, if you like, every list that is a collection of neighbors, I take the length of those, I sum them all together, divide them by 2.0, and then convert it to an integer. Now, why am I dividing by 2? Well, let's think of what this thing represents. Imagine that the words in my word list are like graphs are like nodes in a graph. So imagine like all these, I can just lay them out on a piece of paper, bubbles for each word, one for each word. And if 2 words are neighbors, then there's an edge between them, right? So I have this massive graph with all the 57 words and edges that connect words that are neighbors. So the first question is, how many edges could I have at most? Well, if every node is a neighbor to every other node, then there are n times n edges. More correctly, n times n minus 1 edges, because no node is a neighbor to itself. So there's n times n minus 1 edges, and then I will have counted each one of those edges twice. Because if this node is a neighbor to this node, then this node is also a neighbor to this node. It's symmetric, and since I'm counting all of the neighbors of all of the words, every edge will be counted from either direction. That's twice. So that's where the 2 comes from. I basically count how many neighbors each word has, add them all up, divide them by 2 because I've counted that neighbor relationship twice, once from each end of the edge, and then I print it out in my edges list. All right. So this is my make a network list function. Yes?
So for the arguments in the doc format, you're saying you do the right one first.
So this one here is the first argument to format. It's going to be packed into this one.
Okay, and the second one's for
And the second one here, once you compute that value, whatever it is, it's going to be sent into the first one. The casting to int isn't strictly necessary because, I mean, it's necessary for a different reason that you might think. Notice I'm not turning this into a string. That's automatic. Whatever this value is going to be turned into a string. The casting to int is only because I'm doing division by a float, and I want to turn it into an integer. I could have as easily done this with an integer division if I had chosen to do that.
you can have, so in the format, you can have as many things to do.
Yes, so that's a very good question. Yeah, so for every blank, every sort of Mad Lib style hole in the string that you're formatting, you need to have one and only one argument. So if there are two of these, there need to be two arguments to the format. If there's 7, then you need 7 arguments to the format. Okay? All right, so we're ready finally to play the game. If you remember, the game takes a source word and a destination word, cat and dog, and finds a chain of words where each step in the chain differs from the previous word by one position letter only. And that chain leads from source to destination. So we're going to represent our network with two lists, the list of words and its corresponding network, which is a list of lists. And I now need to find out, if you give me a word, if you say Abakai, 5-letter word, what are the neighbors to Abakai in our dictionary of words? What words do I have in those 5,000 odd words that differ by one letter from Abakai? And the way to do that is to do 2 steps. So let's take a look at what we have here. We're going to do this very simply with a list of 1, 2, 3, 4, 5 words instead of 5,000. These are 3-letter words instead of 5-letter words, but that's the same idea. I'm going to create a network from that word list, and I have 5 words and 2 edges in the network. And if I print out the representation of network, if I ask what the value is, I'll see that the word cat has 2 neighbors, hat and car. The word hat has 1 neighbor, cat. Dog has no neighbors in these other words. Car has 1 neighbor, cat. And foo has no neighbors in this list of words. Now, some differences in this word list from the word list we're using. The first one is, I made this word list up, obviously, and it's not in alphabetical order. There is nothing here that requires that this list be in alphabetical order. My make network function works regardless of how the list is presented. And notice here that it says I have 5 words and 2 edges in the network, but here I count 1, 2, 3, 4. It looks like 4 edges. But what it really means is that cat is connected to hat and car, and that means hat is also connected to cat, and car is also connected to cat. So you can see explicitly how each edge appears twice. Once with the source word on one end, once with the source word on the other end. So you count the edges twice, which is why I divided by 2 when I reported the number of edges in the network. I would have counted 4 here. Divide by 2 means there are 2 edges. Okay? Now, let me just return for a moment to this expression. I turned it into an integer, and I divided it by a float. And what I've done is I've just taken the sum of all of the lengths of those network edges. Do I have to worry about this thing not being an integer when I divide by 2? Let's put this another way. Notice this list here. I claim that the sum of the lengths of the sublists will always be an even number. Always. Why? Because there is no edge that starts at one node and doesn't end at another node. For this to be an odd number, you would have to have an edge that starts somewhere and doesn't end anywhere. So it only appears once. Edges always appear twice. So I can simplify my network edge count by just dividing by the integer 2 with integer division, and I know that there will be no remainder, because by definition, the semantics of this are that the number of edges divided by 2, the number of edges counted this way, will always be a multiple of 2, so when I divide by 2, I always get an integer. All right, let's say I was solving this word puzzle, or this word ladder, starting for the word cat, and I wanted to go to dog. The insight here is that to find the neighbors of cat, I would first have to ask the question, what is the position, what is the index of cat in my word list? And once I know the index of cat in my word list, I can use that integer, which tells me it's in slot 0, 1, 2, 3, or 4. I can use that integer to find the words that are adjacent to cat. So the first step is to find the index of my target word in the word list, and the second step is to use that same index to find the appropriate sublist of neighbor words. Now, you may recall how index works. Index looks at a sequence and scans a sequence left to right until it finds the thing you're looking for. It will return the index that corresponds to the first occurrence of the thing you're looking for. We have an advantage here, and that is that we know that all of these words are unique. So the first occurrence of the word is the only occurrence of the word. So every time I look for the word dog here, I'm going to find it in position 2 and nowhere else. So index returns a 2 for dog, and 0, 1, 2, I find out dog has no neighbors. Okay? So here's my find neighbors function. It takes a word, presumably dog, say, a word list, which is the list of words I know about, and the network, which is the list of neighbor relationships. And it returns the neighbors of word from network by saying, look in word list for the index of the word, and use that to index the network and return it. Very simple. I built the appropriate data structures. You give me a word, I'll tell you which words in my dictionary differ by one character and one character only, if any. Now, this solution was really quite easy, but it's not particularly efficient. And why not? Well, each time I need to find the neighbors of a word, I first have to scan the word list to find the index location of that neighbor, of that word. Remember, I had to scan for dog to find it was index location 2. Scanning the word list takes, on average, if the word is in the list, you will on average have to look at half of the elements to find its location. When we scan for dog, we started at the left and, oh look, it took us 2 comparisons to find it. That's about half of the elements of the word list. If I was looking for the word foo, I'd have to get to the end. If I was looking for the word cat, I'd be lucky and I'd find it right away. But on average, finding the word is on average, it will be in the middle of the list. That's what average means, right? So every time I try to find a word's neighbors, I have to scan word list. It's a linear scan, which on average looks at half of the elements. We say this is an order n operation, meaning that as my word list gets bigger, if I had 10,000 words, it would be roughly twice as slow as the one with 5,000 words. Because on average, I'd be searching twice as many elements. Does everybody understand that? It's very sort of back in the envelope, but just gives you an idea of, let's think about how much work I'm doing. I've got a big list, I'm going to scan it, I'm going to do this much work. I double the list, this algorithm tells me that I will be scanning twice as many words. So it grows time proportional to the length of the list. It's a linear time algorithm. Now we could do better. The same solution could do better because what? Because we know that the word list is in alphabetical order. And because that list is ordered, what algorithm might you suggest for improving the performance here? We studied it. It's the only algorithm we studied that is less than linear time. Ben? It's a binary search algorithm. So I could use binary search to find the neighbor list in time that is much less than this order n. For 5,000 words, on average, instead of 2,800 comparisons, I'm going to do about 12 comparisons. So this same data structure, the word list and the list of neighbors list, can be used to do this word ladder problem in time that is proportional to order log n rather than what we're doing now, which is order n. It's hugely faster. For long word lists, it's going to pay off in a big way. So before I go on, this is a good time to ask questions. Does everybody sort of get that this is a foundational order, not just order of magnitude, but a real change in algorithmic approach that pays off in the amount of time it will take to play the game? Does everybody understand that? So the difference between order n and order log n is huge, provided the list is big. But here's the thing. We can do this even faster. We're going to make this go, it's just like feel like the game show host. But wait, there's more. For an additional $12.99, we can do this a lot faster. And here's how we're going to do it faster. We're going to do it faster. We're going to use a dictionary. Now, why are dictionaries interesting? Because the cost of indexing a dictionary, of finding the value for a key in the dictionary, is not dependent on the size of the dictionary. It is not dependent in scanning. You don't have to do an order n scan. And it doesn't have to be sorted. You don't get to do binary search, which is log n. Instead, it's constant time. This order 1 is like the magic. This is where the magic happens, right? The order 1 says, no matter how big your dictionary will get, it will take the same amount of time to find the neighbors. So if you have a WordNet graph of 10 words, it'll take this much time. I see, just a second. If it's 1 million words, it will take the same amount of time. Question?
So, if the keys of the dictionary are stored in memory, won't you still have to scan something?
You don't have to scan. There's no scanning with dictionaries. The whole thing that makes dictionaries so efficient, there are two parts of this. One is, you'll recall that dictionaries cannot have duplicated keys. Every key must be unique, right? Every key is unique. And then because every key is unique, we build an internal data structure, which you'll get to in CS2, where all the magic gets revealed in data structures. We'll build a data structure that uses what's called a hash function that maps the key you give to some number. And then we use that number to go immediately to the location in memory where that object can be found. So the function itself is what does the magic. The hash function itself is what does the magic. Okay? Trust me, it really is order 1. All right, so if our word list and network can be replaced with the dictionary, everything will be faster. And basically the idea is, when you make a network from this, what I want to get back is a dictionary where the elements are the original elements of this list and the values are the neighbors to that word. It is a very natural representation. Instead of carrying two things around and, comparing them, I have this one package that says cat, car and hat. So cat, where's cat? Cat, hat, and car. Of course, the order in here doesn't necessarily correspond to this order, but we don't care. Because given a word, I will immediately find in one operation its list of neighbors. So here's my new make network function. It is a little bit more tedious. You'll notice that the cost of making the network will turn out to be the same as making the network the first time. So the cost of constructing the data structure is the same, but the way I go around it is a little bit more tedious. So let's see how we did it. So I'm going to do some things differently here. First of all, I'm going to keep track of how many edges I find sort of online as I construct this dictionary. And I'm going to construct a dictionary word by word. I'm going to start with a dictionary that is empty. So in other words, this is a dictionary comprehension. It collects the word, an empty list for every word and word list. So this is the initial dictionary, is just the set of keys, each associated with an empty list, a fresh empty list. And then what I'm going to do here is I have a nested set of loops. I'm going to let I go over the range of length in the word list. So I will index all of the words in the word list one at a time. And then within that loop, I'm going to let j index the words that follow I. So the way to think about this, I have a list of words. The first index will scan all of the words. The second index, starting wherever the first index is, will scan the remainder of the words after the first index. The reason I'm doing this is because I know that whenever I encounter word I and word j that are neighbors, I can add the edge from I to j, but also the edge from j to I in one step. So let's see how that works. So if the ith word and jth words are neighbors, I'm going to append the jth word to the network representation for the ith word, but I'm also going to append the ith word to the network representation for the jth word, and I will have added both of those directions in one step, and I will count edges plus 1. Then the same statistics here, but I don't have to do any computation because I've been keeping track, I've been counting as I go through the loop. And then finding the neighbors of the word becomes even simpler because now I just have the word I'm looking for and this network which is of type dictionary, and all I have to do is return whatever is indexed by word in that dictionary. So if I make this network, I get this thing, and the search is exactly the same. So now I have two implementations. I have an implementation with a list of words and a corresponding list of neighbor lists, and I have the implementation with the monolithic dictionary that maps words to its neighbor list. These are two equivalent approaches to playing the game. We're going to explore their relative performance. So the next step here is to search the word list for a word, solve the puzzle basically. So this is kind of the fun part. So the key idea here is that we're going to play WordNet. One of you is going to give me a source and a destination node from the list. And I've got to find that ladder of words that takes me from source to destination via a series of single character transformations in the words. And the key idea here is to start at the source word and like dropping a pebble in a lake, we're going to radiate out and we're going to look at the neighbors of the source word and then the neighbors of the neighbors of the source word and the neighbors of the neighbors of the neighbors of the source word until I eventually find the destination word. And because I'm extending my ripple by one word in the ladder every time in every direction, the minute I find the destination word, I will have found the shortest ladder of words that connects the source to the destination. And if I'm unlucky enough to ripple my way all the way through the graph without finding the destination word, well, then there is no ladder that connects them. So let's see how this works. I'm going to make this work by having two lists of nodes that I'm going to keep track of. I'm going to have a list that keeps track of the words that I've looked at. I'm going to start that list with just the source word on it, the word I begin with. And then I'm going to have a second list of words called the pending list, which will contain initially all the neighbors of the source word, but I will manipulate that list by adding the neighbors of the neighbors and the neighbors and the neighbors of the neighbors and so on. And I'm just going to keep doing my search until I run out of nodes to search. So this is a little bit more simple to see graphically. So we're going to do this graphically before we come back today. And then we'll come back after spring break and do it in code. But the general idea is I place the source node in my pending list. And then each time through my main loop, I take a node off the pending list. This is a neighbor. I move that node to the explored list, and I put that node's neighbors on the pending list if I have not yet seen them. So I have to do this little extra thing that says I'm not going to look at a node more than once. I'm only going to add the node the first time I encounter it. It's a little bit more obvious when you see it graphically. So that's the code. Let's take a look at what it might look like. So here I have what looks like a word network, except that instead of words, I just have numbers on the nodes. It lets me sort of talk about it by number. But you should get the general idea of this algorithm when you see it. So here's my source node, 2, and I'm looking for destination node 11. So I want to find a path that goes from 2 to 11, and there's a bunch of them, right? There's many paths. In particular, I would like to find the shortest path, if I can. You know, it's probably not this one, right? The shortest path will be 1, 2, 3 nodes long. That's the one I want to find. Don't want to find this one. I certainly don't want to find the one that goes back through 2 more than once and uses all the nodes. I want to find the shortest path. And I'm going to do this by having my pending list and my explored list. Now these are just sets of nodes, so I'm going to use set notation. Those aren't dictionaries, they're just sets of words, or sets of node labels. And I'm going to start by putting the source node label in my pending set. And now each time through my loop, I'm going to randomly choose an element from the pending set. I'm going to move it to the explored set. And I'm going to take the neighbors of the node I'm manipulating and add them to the pending set, if and only if they're not in explored or pending. So, first time through the loop, 2 has which neighbors? It has 1, 6, and 3. These are the nodes that are reachable from 2. So I'm going to move 2 to the explored node. I'll color it red to show that I've explored it already. And the pending list will now have 1, 3, and 6, which are the adjacent nodes to 2. Everybody see that? Pretty straightforward, right? Next time through the loop, so I have this loop that I'm working on. Next time through the loop, I'm going to choose one of these guys at random. When I take a node off the pending set, I'm basically going to explore that node. So in the graph, I take the node off, and it's like I'm standing here and looking at the adjacent nodes. So I'm going to choose to explore node number 6. Doesn't matter which one of these I explore. I'm going to choose at random. I happen to choose 6. I move 6 to the explored set. I color it red because it's explored. And now I look at the nodes that are adjacent to 6. There are 2 of them. Well, there's 3 of them because 2 is adjacent to 6. So I'm going to add 2, 4, and 9 to the pending list, provided they're not in the explored list. So 2 is in the explored list, so I'm going to ignore that one. I'm just going to add 4 and 9 to the pending set. Okay, so far? We good? Next step, go through the loop again, take a node off the pending set at random, move it to the explored set, and inherit its neighbors. I'm going to take node number 2. Where is 2? Node number 3, right up here. Notice that 3 is not a neighbor of 6, but it was a neighbor of 2. So I'm going to go back and take a different neighbor of 2. And I'm going to put its neighbors, 4 and 7, on the pending list. But wait, looks like 4 was already there because it's also a neighbor of 6. So I get to 3, 4, and 7. Well, 4 I don't need to worry about because it's already there. I add 7. And of course, 2 I don't need to worry about because it's on the explored list. So I keep going through the loop. Next time, I'm going to pick node number 6 as my explored node. That brings node 9 into the pending list. Next time, I'm going to pick node 9, and that brings 10 into the pending list. Next time, I'm going to pick node 7, and that brings 11 and 8 into the pending list. And now what happens here is I look at the pending list before I pick my next node, and I find, whoa, 11 is my destination node. It's there. So whenever 11 appears in my pending list, I know that I have found some path that takes me to node 11 from node 2. So this first attempt at playing the game doesn't actually find the path. What it does is it answers a question. The question it answers is there a path from node 2 to node 11? Is that path possible? So we would know if we had our word list using this game that there is no path from cat to dog. But there is a path from cat to hat. So this version of my game actually returns false or true depending on whether a path is found. This is the very first approximation to our game. It just says yes or no if the path is found first. And secondly, notice that this solution just guarantees that a path is there if it returns true, but it doesn't say anything about the length of the path. And in fact, if you think about it, the way we found node 11 was when we expanded node 7. And we got to node 7 this way. Well, actually, we could have gotten it this way. So this is the shortest path. We might have found the shortest path. But we didn't make any effort to do that. We could have as easily run this algorithm and found a much longer path. Doesn't matter, because this first version only says yes if a path exists and false if no path exists. Now we're going to dress this up after break. We're going to alter the algorithm so we can guarantee that it's always the shortest path we find. We're going to dress up the algorithm so that we can also, once we find the path, tell you what that path is, all right, so that we know how to get there. And then that will have solved the word game. Okay, any questions? This is a convenient stopping place and we're sort of out of time. So I'd like to leave it here and then we'll go away and come back after spring break and pick this up and finish it in a day or two. And we'll go on to some other problem then. Have a good break, relax, get homework 1 done, and you can enjoy the rest of your break.